Okay, so welcome back to another lecture of EE 2080 Microprocessor Systems Design and Interfacing course. So, hopefully, all of you are working on your 8-bit microcomputer in Logisim and doing quite successfully. Hope you are able to appreciate the importance of designing a microcomputer from scratch. Hope you understood the components thoroughly, how the interconnections are done, and how everything can be controlled using instructions like add, sub, uh, out, etc. Right? So now time has come. Now we'll just move on from that 8-bit microcomputer to the world of modern processors. And particularly, our aim is actually the uh, Cortex M0 Plus processor. Okay, so let's move on. So this was the 8-bit microcomputer that you were building, and I hope each and every part of the circuit and each and every thing that these operations do is very clear to you, and that's very important. Now I would show you another instance of an expansion of this particular circuit, whatever we built, and this is actually in the textbook referred to as the simple as possible computer 2, SAP 2. So if you see here, quite a lot of extension, right? There was no input interface provision in our simple 8-bit microcomputer, but you do have that option here. Let me just it's basically the input interface option that they are giving. Program counter was known to us. Memory address register was also there. The RAM was also there. Then now, yeah, this is interesting. So now what they did actually is they have a data address register, or what you call, yeah, exactly. So or rather in fact not data address register, but a data register where the output of the memory can be stored separately. Earlier it was like directly going to the bus. Now they do have a separate register for that. Then of course the instruction register is there and the control unit will come here. And on this side, accumulator and register B, instead of that they're calling it as temporary register. And then of course the ALU is there, and then of course there is an option to flag, for example, if your addition is overflowing. Okay, so your carry bit is coming, then it's an overflow, and then of course you need to sort of give that input or that sort of warning to the user, right? So that's typically done using flags. You might have also used so many flags in your C program, for example. So similar concept, but that's again registers, right? In this case, maybe it's 2 bits, so we can consider this as 2 flip-flops. Okay, then you have additional registers like B and C. So let me actually mark which are additional. Okay, so you do have something additional here, and of course the size part will come back in a moment. But then of course you have these registers which are additional. This is also additional, and then of course we had one output port, but now we have another additional output port. So that's the thing. So you have a provision for some serial interface as well, serial in, serial out, right? All these things you will study in detail when you study about the serial interface, when we discuss those aspects in interfacing aspect in detail, okay, later on. So definitely this is much improved hardware compared to our simple 8-bit microcomputer. And in addition to that, if you see the bit size, the program counter is now 16-bit in the case compared to our 4-bit actually. The reason is very simple, because your memory is 64K. So what is 64K means? Okay, very important to understand that, right? So 64K, if you want to put this way, this is something like 64 into 1024. That means 1K is equal to 1024 bits. So this I can put in terms of 2 to the power, because we generally have each bit is 1 or 0. So you have 2 raised to, this one comes to 2 raised to 6, correct? 64 is 2 raised to 6. And then of course this comes 2 raised to 10. So that totally is 2 raised to 16. And then you have 16. So 2 raised to 16 locations you have in this 64K memory. So 64K memory means 2 raised to 16 locations. So how many address bits you require is 16 bits, correct? And that is what you are actually seeing it over here. Okay, so 16-bit address is because of this guy. Okay, I hope it's very clear. Okay, so that's a major change. And then of course, let me clear all this. Okay, all inks are erased. So these are the additional changes I just highlighted. Two input ports, a 64K memory, a memory data register, then 4 registers now. So ALU with flags, that's important. 2 output ports as well. And you see the instruction. Yeah, this is, we had only add, sub, out and halt, right, in the previous. In fact, LDA add, sub, out and halt. But now if you see here, so many instructions are there, and you are lost now, right? And you also see the opcodes. Earlier it was very simple 4-bit opcode. Now it is basically you have 4 plus 4 8-bit opcode which is coming out. So this memory location, 64K locations are having 8-bit as the output, and the important thing is like the instruction itself is now 8-bit. Earlier it was how many 4 bits, right? Now it is 8-bit. So you can see it over here. Add B, for example. So this is a complete instruction now. Add B is 80, add C is 81. So you can easily decode that add is nothing but 8, and B and C are denoted by 0 and 1. This is hexadecimal again. So 8 is, always remember that 80 implies it is 1, sorry, yeah, 1000. 0000. That is standing for your 8. The entire thing is standing for your 8. I'm sorry. The entire standing for 0, 8 and 0. So this part stands for 8, and this stands for your address, which is B in this case. So everything actually is very complex now, and imagine that you are going to build this circuit even in Logisim. I'm sure you are complaining about building your 8-bit microcomputer, the simple microcomputer in Logisim. I'm pretty sure, because so many connections, so many things that you have to be careful about. And now you think or imagine that you're building this particular circuit, this entire circuit, whatever you're seeing over here. This entire circuit, you're building it in even Logisim. Okay, it's so complex. And then of course, coming up with a control unit to execute all these instructions, it's even more terrible. So that is why we started off with that 8-bit microcomputer to make you appreciate the complexity in building that circuit and building the control unit. Building this, if somebody is very keen, please do that. Please make your hands dirty. You do all these in Logisim. You forget about doing it in Verilog or using logic gates in a breadboard. That is a gone case. It's very, very difficult for you. But if somebody attempts that, somebody builds that, then nothing like that. You will become an expert in the hardware design of a microprocessor. So the major takeaway from this slide I want to let you know is building such a circuit is so intensive effort. So it takes maybe months and years to build that, to make it robust, to make it stable, and then of course design a control circuit itself will take months. So that's why we are not going to build a modern day processor from scratch. That is beyond our scope, and that is the reason we built a very simple computer, so that you appreciate what is inside. And now in this course, we will only understand the architecture, not even at the level of this many details, but we will understand what are the components inside and how it is laid out and all those things. That forms one aspect. And then we quickly move on to the instruction set supported by our microprocessor. And then of course, do some programming using these instruction sets. And even for that, you have a very sophisticated software tool that we will be using. So you don't need to actually build anything from scratch. You are more like a user from now onwards. Okay, so with that, hope you understood, appreciate the efforts people are doing all over the world to come up with those microprocessors for you. And then of course, to lay out these control units for you. All you need to worry about is writing some instructions. You come up with a program, you load that program into the memory, and then you switch on the computer, it just does that for you. So you don't need to. So all your efforts can be put on the program writing. So that is the important aspect that I want to convey. So it goes back to the initial statement I made. A microcomputer, a microprocessor, or a microcontroller is a fantastic device or a system where you change the software, the functionality of the hardware is changed. So you can concentrate from now onwards on building that beautiful softwares. Okay. So with that, let's start. Okay. So some history. It's very important that we appreciate our ancestors, right? Whoever contributed to all these easiness that we are experiencing nowadays. So the concept of microcomputer way back in 1930s, 1936 to be exact, Alan Turing, he was a theoretical mathematician you could call. So he proposed this concept of a universal Turing machine. And the concept is pictorially represented here, where you have a computing machine and then you have a magnetic tape, and all you need to do is store your instructions in this magnetic tape, and this computing machine will read them. Input and output also are there, and then does the operation, and of course you can store the output back on the tape. So this was the concept introduced by, of course this is much complex than that. Somebody is interested, please search for Alan Turing's universal Turing machine. You will come to know about that. And it's more theoretical concept, but definitely worth looking into it. Okay, but the concept that he proposed way back in 1930s, which was even the time when electronics was getting popular, the transistors and all those things came much later in 1940s. But Alan Turing proposed that his dream machine, which is, he called it as the universal Turing machine. And the idea was like this: the same hardware can do different operations based on various softwares. So you just change the software. So it's like a software operated hardware. So hardware is designed first, and then it will have certain capabilities, and then you provide the software which could actually do a lot of operations on that hardware. So this was the concept Alan Turing introduced, and later it became practical through this great person, John von Neumann. That is what we call the Neumann architecture. Hopefully all of you remember what is Neumann and what is Harvard architecture. If not, please always remember that. Neumann means only one bus which carries both data and address. Harvard means you have two separate databases, two separate buses for data and address. So the concept Alan Turing proposed was made into practice by John von Neumann. And of course, he called it as a stored program computer. Okay, so this is the history. So those who are very interested, please do further search on this and get enlightened. Okay, so let's move on. That's not the important part that we want to spend a lot of time on. So microcomputer, again, this is just a revisit. I hope you are very clear, crystal clear on what exactly this terminology means. So whenever you hear this term, immediate thing that you have to consider is, or come to your mind is, there is a microprocessor chip which is sitting there, and this chip, what is inside, we will discuss again, we will revisit again in the next slide. But before going there, this microprocessor has ideally 3 buses, address or data bus, and then the data bus. So this can be combined as a single bus based on the type of architecture, whether you are following a von Neumann architecture or whether you are following a Harvard architecture, they will be same or separate. And then of course there is a control bus. Don't forget that. That is the brain, right? So don't forget about that. Of course there is an interface, and that interface is basically dealing with memory. So you will have all these things is still vague to you. This is the expansion of this is electrically programmable read-only memory. So EEPROM. So all these things we will study. This is where the things that you want to basically do every time a computer is switched on is what written into here. Because you can't really change it on the fly when the system is operating. You have to program it separately. Okay. So this is sort of a read-only memory, which is a constant memory, which will be erased maybe once in a lifetime when you change the BIOS, for example. Okay, so that is the memory here. And then this is actually outside of the microprocessor world. You need to interface that with the microprocessor. And then of course the RAM is there, which is what you use on the fly for all the calculations. And then a lot of input-output interface devices you need to connect. For example, the calculators, the keyboards, the mouse, or any other memory. For example, you do have some SD card memory and all those things, right? All these come at the interface. So the basic takeaway is like a microcomputer is consisting of so many small components, which one of them will be microprocessor, others will be memory, then you have a lot of interfaces. So that is a concept that should go into your mind. And then of course, as far as the operation is concerned, the two important aspects that you want to actually consider here. One is definitely the operation part, which as I said, you will be concentrated on in this design. And then of course these two terms well known to you by now, because this essentially form the control unit design for you, right? Fetching part, of course you know that there are two aspects to fetching part. One is fetch the instruction from the memory to the instruction register. That's the aim of this process. But then of course there's another one which is actually, we already saw that, increment the program counter so that it is ready and store the address for the next instruction. This I am talking about in the fundamental operation, which is a sequential operation which you will learn more when we go to that again for the microprocessor that we are going to talk about. But remember, this is a usual routine, this part. But program counter, just we will, I think that comes again. So we'll discuss that when that portion comes up. Okay. So at this point, fetching cycle should be very clear to you. Then execute cycle is the cycles that where the actual execution happens, right? So that means based on the instruction, you do certain set of operations. That's the meaning of it. So don't forget our small 8-bit microcomputer. Fetching had 3 cycles, 3 clock cycles, and execute also had 3 clock cycles. The total number of cycles that was required to have this fetching and execution operation to happen was 6 clock cycles in our small microcomputer. But it may be entirely different for a microprocessor that we are going to study. So it all depends upon how you design, right? But remember, underlying there are 2 cycles like this, one for the fetching part and one for the execution part. Slightly more details here. So this is the memory. So basically you do have a program memory and a data memory. Remember our RAM where we divided it something like this for the experiments. And then of course there is a memory address which is given here and then memory output here. So fetching essentially means, so you have the program counter output which is coming as the address, and then this memory output will get fetched into your instruction. That's the thing. Right? So that's it. I hope I need not explain it again because it's quite crystal clear to you. Okay, so the program counter default is basically incrementation. So whenever you, after this fetching part or during the fetching part, the typical operation is you increment the program counter by 1. But sometimes this we didn't even have it in our 8-bit microcomputer, but this happens in the case of a modern day computer where I already explained to you during one of the live sessions about the concept of interrupt. Or your program may have something like jump, right? Branch operation, some for loops, some if loops, etc. So in those cases, you may have to actually change the address to some other location. It's not the typical memory location of the address. Okay. You may have to have a new address where your branch operation is going to happen. So don't worry if you're not understanding, because we will understand this in detail when we talk about those. Okay. So please remember that program counter not necessarily always increment by 1. It can have a new address which is actually pointing to an address location where your branch operation is kept. So you will have some branch of, you write that in C program, right? If this happens, this has to be executed. So there are certain set of instructions. So what I'm saying is, let's say this one. Yeah, let me use the pen here. So let's say you have an if loop and then some condition here and then certain instructions you, right? So if this is satisfied, you have to execute these set of instructions. So there is an address here, right? So that is what I meant here. So if there is a branch operation is triggered, then the program counter should not be incrementing by 1 and storing the next address, because I don't want to execute that instruction. I want to execute certain fixed set of instructions, and it will have a memory, and that address should come to the program counter. So we will understand how that will happen. Okay. But overall, fetching is basically the operation where the address or the instruction has to be fetched to the instruction register. Okay. So that's a key takeaway. And of course, in executing, this is what based on the instruction. So it may be some arithmetical or a logical instruction. And then of course, which memory address to access. That is what I was talking about in the previous. So that's also very important. So let's not spend much of time, because it will definitely get repeated when we talk about this in detail later on. Okay. So execution, again, accessing the registers, instruction register basically, and of course the memory. So that's it. So microprocessor. So we talked about microcomputer and the fetching and the execution cycle, but now let's concentrate on the microprocessor aspect alone, because next few slides are revisit for each of these components. So inside of this microprocessor, if I put a microscope on the microprocessor, you will find out it will essentially has an arithmetic and logic unit. It will have section of registers, so many registers, And then of course the control and timing, right? Timing is the clock and the clear and the control unit. This essentially forms the microprocessor. So this will be a single chip solution which sort of abstracts the arithmetic and logic unit, the registers, and the control and timing section. So the key takeaway is there is no internal memory other than the registers. That's very, very important to understand. And then of course you have the interface, whether you have either separate address bus and database or one bus which sort of uses for both address and data transfer. And then of course control bus, again don't forget, bus is nothing but a set of wires. Don't get confused. Now let's actually revisit each one of them in slightly more detail. It's not really, again as I said, we may not actually revisit them in again this much detail because we treat the microprocessor as a black box from now onward. So but inside of this you already know arithmetic and logic unit. It does the arithmetic and logical operations, and typically, very, very important, typically if you're going to work in this space, ALU is the first hardware design that you take up when you are going to design a new microprocessor, because it is the sort of the brain, or I would say the not brain, the functional part of your circuit. Brain is always a control unit, right? So this is like maybe heart, for example. Okay, so what essentially here, maybe this is just a sample I've taken. So you figure out what is this operation. It's definitely a 4-bit because you have B0, B1, B2, B3 and A1, A2, A3, right? And A0, A1, A2, A3. Sorry. So it's a 4-bit operation. So it's a 4-bit ALU, but our modern day computers are talking about 32 and 64 bits, right? So this is a very simple circuit I've just taken and for illustration. So always remember that your arithmetic logic unit, if you dig deeper, it will be always a digital circuit with gates. And if you dig deeper to the gates, you will end up in transistors, right? So that is the beauty about it. But we are abstracting it. We abstract gates. We abstract transistors by using gates. We abstract basically logic circuits using gates. And then of course, slightly higher, we abstract a lot of these ALUs, right? So if you dig deep inside, finally you will end up in gates. That's it. Okay, so that's it. I hope it's crystal clear to you. And then of course, control unit is the circuitry. Again, it's a digital circuit at the back end. Don't forget that. It may have memory. For example, we designed our control unit, the 8-bit microcomputer control unit, using memory. But that is not mandatory. You can come up with purely digital circuit based approach. Okay, but the overall architecture actually interesting now. If you go back and relate this architecture, whatever I'm showing you over here, to the architecture that we designed, you can actually correlate. Okay, so for example, we definitely had a clock because we are talking about a synchronous digital system. So it is all clock driven. Everything happens on the clock cycle. So we already know that. We had a ring counter which we could actually correlate to the step counter here. And then of course a decoder for the ring counter as well we had. And then of course the instruction register, the instruction was coming to the instruction decoder. We also had that memory, if you remember. It was a ROM for us. And then of course these two inputs were coming together for us also in the encoder. And then of course the status flag and all we never had. This is important for a modern day computer because if there is an overflow or if there is a negative, something we need to do, right? The control unit need to do some operation. That is why this also comes as an input. And we also had an encoder which actually gave us a 12-bit control signal in our case. Okay, so you can now correlate. This is the control unit of a modern day microprocessor, but you can easily correlate the same blocks with the blocks that we developed in our 8-bit microcomputer. So that is a beauty. So that is the reason why I purposefully made the course, structured the course like that, so that you get a feel of what is inside, how it is done. If I had introduced the control unit like this, you would have, oh, what the hell it is going on, so many blocks. But now you can appreciate it, right? Why we need so many blocks. I need not actually explain to you what each and every block stands for. Okay, again, this is dependent on your microprocessor. It may change, it may become more complex or less complex depending on your microprocessor. Okay, so moving forward, so we discussed about ALU, we discussed about control unit, and then of course we need to discuss about registers. So registers are actually basically, if you go inside, it's a set of arrangement of flip-flops, right? They are expensive memory compared to a RAM or a ROM or a PROM or a flash memory. that we will discuss at some point. These are expensive, but you do have bunch of registers, not just 2 registers like in our 8-bit microcomputer. You will have a bunch of registers, and the primary purpose, I highlighted it in bold here, it is to temporarily store your data or program. Okay, so that's a purpose. The number of registers will depend upon your architecture. Okay, so there's no hard and fast rule saying that you should have 2 registers only. You should have 7 registers only. Nothing like that. Okay, so this is an example. So Intel 8086 is an 8-bit microprocessor, one of the all generation very popular Intel processor. And you can see over here so many registers are there. So you do have some general registers. So this is H means the high bit and L means a low bit. So this is a register, this is a B register, there is a C register, there is a D register. So you do have high and low registers. They are individually accessible as well based on the memory location. And then you do have, in fact, this is 16-bit. Sorry, I said 8-bit, right? It's a 16-bit register. So this is more significant 8-bit and this is least significant 8-bit. So each one can be accessed as together as a 16-bit, or it can be accessed individually as 8-bit. That's why we are showing it as a block. And then of course there is some index registers S1, D1, which will be accessed as 16-bit alone. So those are actually very, very important. So you can see it over here. So some pointers and some index register, source index, destination index, source stack pointer, base point. Don't worry about all this because we are not going to study about Intel 8086. We are going to study about ARM Cortex M0 Plus. So that is a different architecture layout altogether for that. But that also will have a set of registers. So the key takeaway from this slide is the registers, the number, their layout, everything is dependent on the architecture. Okay. So in this case, I'm just showing the architecture for an 8086 microprocessor. How does the register layout look like? And then as I said, there is something which is very important, this IP, which is basically sort of a flag register. So you have so many flags here, okay, based on some operation. So a list is here. Again, no need to spend a lot of time here because we will have a detailed discussion about the flag registers when we discuss about Cortex M0 Plus as well, because this is specific to Intel 8086, which is not relevant to us, because if you are going to use 8086, of course, you need to understand this correctly. But our use case is more on the Cortex M0 Plus, so we will talk more on the flag registers associated with Cortex M0 Plus rather. So we will not spend much time here. Okay, so let's skip on. Okay, so we will move on. So I hope there is no issue here. And this is all self-explanatory, but as I said, don't worry. We will again take up as we take up the flag registers for Cortex M0 Plus. But just to give a inference here, so Z flag basically means 0 flag. This happens if the result of a mathematical or a logical operation is a 0. So let's say you are subtracting 2 operands and your result is 0. Then this flag will be set to 1. And then the microprocessor control unit will come to know that a 0 has been done. So this is used for many purposes. For example, you have an if loop. And if you're comparing 2 variables, A equal to B. So essentially what is going to happen at the back end is you do A minus B. And if A minus B is equal to 0, your if loop is satisfied. So this flag will be set and then control unit will have to trigger some operation so that it will switch and execute the instructions which is written under the if loop. So that is the meaning of it. Okay, so that's the importance of it. I hope I'm able to convey the meaning of it. Okay, but we will see all this. You have a lot of experiments in the lab. And maybe we will release the kits to you so you can take that home to hostel, you experiment with it, you become very thorough with it. But the key takeaway again, there are certain registers which are flag registers which was not available in our 8-bit microcomputer, the simple 8-bit microcomputer that we designed. But these are very essential building blocks of a modern day processor. And what they do is actually they will alert the control unit with flags. Okay, for certain operations. Again, you can see carry flag, literally it means what it means. There is a carry being set. There is overflow flag, which means addition is overflowing. Your carry bit is also overflowing. That is the reason for this. All these things are very important. And then of course, interrupt, I briefly explained, but we will have a detailed session on that later. Okay, so program counter. This is again a sort of a counter which is part of the microprocessor, and we already know what it is. Again a register, that's why we didn't put it separately, but there is some importance to program counter, right? Because it is the address for the instruction, next instruction. So you can treat that way from now onwards. Program counter will store the address of the next instruction to be executed all the time, irrespective of whether it is sequential one by one operation, or it is an interrupt operation, or it is a branch operation, whatever it is, this will have the address of the next instruction. So the control unit will always fetches the instruction based on the program counter address. So it will fetch the instruction from the program memory to the instruction register. Which program has to be fetched, which instruction has to be fetched is determined by the program counter. Okay, so a old generation program counter, so IBM machine was a mechanical program counter which is looking like this. So you can see it. So here manually, I think one of the Logisim experiment where I was actually setting up the address manually, right? You can do that. So here you can actually do that. So this is, if you search around for IBM 701, there's a lot of history around it. So please do that in your leisure time. This is the way you get motivated to the subject, right? The way we progressed from being a mechanical program counter to a digital program counter using a register. All these are fascinating stuff. So please have a look at them. Okay, so not much use in programming actually, because while you write a C or assembly language programming, there is no explicit control on the program counter because it is decided by the control unit, and it is just like an indicator, just like this here. You will come to know what is the value of the program counter mechanically here, for example. Okay, but that's not the case. Ours is digital. So purpose. So some of these statements are still unknown to you, but you will understand it as we progress in this course. So one of them is very clear to you. A very simple statement of program counter is it stores the address of the next instruction. Okay. There are other use cases as well for program counter, which we will discuss as and when the time comes. Okay. So for example, the stack is the memory where you do store. It is like the RAM memory that you store all your operations in. It can even store the address of the top of the stack. Okay. So this part is already known to you. Store next is already known to you. Count the number of instruction. Wow, that is something which is also very, very interesting. To store the base address and top address. So it is also used intermediately for some purpose, which you will discuss later, not now. But at this point, one thing pretty sure for you or pretty important for you to understand is it will have the address of the next instruction. Okay. And then, of course, last but not the least is the bus system, which is the interconnect. Okay, so there is three type of bus. I need not bore you again and again with this. Data bus, which is bidirectional. Address bus, which is unidirectional, because data bus you have to write to the bus and read from the bus, right? That is what meaning of it is. Because you need to write the data to the memory and read data from the memory. But address is unidirectional because you only write or load from the bus to the memory, right? Or the memory address register. There is not the other way. That is what the meaning of this unidirectional aspect. And then of course, don't forget the control bus. It is also a bus. And what is this bus? How does it look like? If you open up your desktop motherboard, you will see something like this. So this is also classical example of bus, but it is of course the PCI interface, but this is what we name it as bus. So from top to bottom in this case, so this is a cross 4 in the sense like it's a 4-bit or 4-bit sort of connection here. And then of course a 16, not 4-bit, it's 4 lanes actually. So 4-line connection here, 16-line connection here, then only 1 line here, and then 16 line here again. So this is actually a 32-bit PCI, which is actually shown over here. Okay, so this is, if you are more interested in this, we are not going to study about PCI and all because it is more at the computer level. We are still at the microprocessor level in this course, but I thought we'll introduce the concept of BESS through PCI because it's quite common to you. And always, when will you use PCI connections? For high-speed data connections, right? For high-speed data transfer is what typically you use the PCI slots for, or PCI buses for. So within the microprocessor itself, you do have these connects, you do have these wires which will transfer the data, the address or the control for you, and those are typically we call with a fancy name bus. Okay, so that's it for this lecture. And now I have a small memory design problem which is coming, which we will take up in the next lecture as a short lecture. Okay. So this is an interesting, so it's, you can treat this as a tutorial, this particular lecture, which is, okay. So till that time, it's bye from my side. See you in the next lecture. Thank you.